In the last video, I did a few problems on rings, and let's continue now. I'm going to do some more problems in this video. In the third problem now, last time we did two problems. Let's introduce a very important construction in ring theory. This will be useful if you continue studying ring theory. So, so I'll introduce it to you and do some simple properties. So let R be any ring, and let me remind you again that in this course, a ring for us means a commutative ring with unit. Let S be a subset of R. I'm not asking for it to be a subring, only a subset. So we say that S is a multiplicative set or more suggestive name is multiplicatively closed, or S is multiplicatively closed so that's the another term for this. If the following happens, if two things happen, one is in S, the identity element, multiplicative identity element of R is in S. The other is if A and B are two elements in S, for any ring elements that are both in S, their product is in S. So it's multiplicatively closed, as the name suggests. If two things are in S, its product, their product is also S. Okay, that's all, no other condition. So immediately you know that, for example, it cannot be if it's an ideal, it has to be the unit ideal, because one is there. If this property, if it's an ideal also, then it must be equal to R. So most of the time these are not ideals, or any kind of closure under addition will not be there. So in quick examples to you. So if R is Z, you can take S to be odd numbers, right? S1 is odd numbers. So 1 is an odd number, product of two odd numbers is odd number, so this is multiplicative. S2 even numbers. This is not multiplicative because even though the product condition holds, if two even numbers multiply to an even number, but one is not there. So that's an important condition for us. So it's not multiplicative. Let me just one more example. Numbers not divisible by 3, or this is multiplicative. This requires a little bit of thinking, but you can show that this is a multiplicative set because 1 is in this set, because 1 is not divisible by 3. It is in this set, whereas, and if two numbers are not divisible by 3, for example 5 and 7 are not both divisible by 3, 5 times 3, 7 is not divisible by 3. Here the important fact is 3 is a prime number. If 3 does not divide A, 3 does not divide B, then 3 does not divide AB. Remember, that's a property of prime numbers, because if 3 divides AB, 3 divides either A or B, 3 divides B. So this is multiplicative. In general, we can define S4 to be numbers not divisible by a prime P. This is multiplicative. Right, because exactly the same idea as before. 3 is a prime number, you can replace it by any prime number. What about numbers not divisible by 4? Say this is not multiplicative because 1 is there, that's fine, but 2 is there in S5, but 2 square is not in S5 because 2 is not divisible by 4. However, 2 squared is 2 times 2 is divisible by 4, so it's not in S5. So this is why you need a prime number in this case. Okay, so 4 is not prime, so this is not going to work. More generally, if you have an integral domain, you can take S to be R minus 0. So all non-zero elements of S are. Right, this is multiplicative also, because you multiply two non-zero numbers, their product is non-zero. So if two elements are in R minus 0, their product is also in R minus 0. This is multiplicative. Remember that this will not be multiplicative if R is not an integral domain. There will be two non-zero elements whose product is 0. So that will not be multiplicative. One more example I will do before continuing. Let's take Zx and let's take f to be all polynomials in Zx such that f of 0 is not 0. This simply means the constant term is non-zero. Right, because f of 0 is the constant term of any polynomial. Suppose it's not 0. 1 is certainly in S because constant term of 1 is 1, which is not 0. If f and g are in S, then f of 0 times g of 0 is non-zero, because f of 0 is non-zero integer, g of 0 is a non-zero integer. That means the constant terms of f and g are non-zero integers, their product is non-zero, so f g is in S. Okay, so this, hence S is multiplicative. So this is another example of a multiplicative set. So these are some examples of multiplicative sets. Now the point of the problem is not this. The problem is to show that there is a new ring. We can construct a new ring. So actually now I will assume that, so I should have said this before, assume, for simplicity this can be done in general, but as a first introduction to this, we can assume that R is an integral domain. From now on in this problem, we will assume that R is an integral domain. We can construct a new ring which we note by S inverse R, which contains R and where every element in R in S is a unit. So I will explain what this means. So more generally, there will be a function from R to S inverse R which is injective. Image of an element of S is a unit in S inverse R. So this process is called localization, and what we are doing is we are forcing every element of S to be a unit. In general, of course, when you take a multiplicative set, the elements are not units. In these examples, you can see that odd numbers are not units. 3 is not a unit in S1. So, however, we can construct a new ring where it becomes unit. So, we define S inverse R to be, so please keep in mind when I am doing this, the example of how we construct rational numbers from integers. We have integers and we take ratios. In S inverse R, we take ratios where denominator is in S. So, simply it is defined like this. A by S, they are just symbols at this point. A in R, A and S are both in R to begin with, and S is also in S. So we define this, and as equality will be, A by S will be considered equal to T if AT is equal to BS. Just like we have two rational numbers, 1 by 2 is equal to 2 by 4, because 4 equal to 4, the same idea I am applying. So two ratios are considered equal if their cross products are equal. This is the set. Addition on this, again we are exactly mimicking the construction of rational numbers. So addition is A by S plus B by T is AT plus BS by ST. Here is where the multiplicative property of S is important. S and T are in S because, and hence their product is in S. So this is in S inverse R in my notation. So multiplication is also defined in the same way. A by S times B by T is A by B times ST, which is in S inverse R. So important to point is, if ST are in S, S comma T is in S, ST is in S. So that is what we are using. One can check that this has all the required properties. 0 element is 0 by 1 or 0 by any other element. Multiplicative identity 0 element, remember, is the additive identity. Multiplicative identity is just 1 by 1. 1 is in S, remember, so we can put 1 in the denominator. So with this and this, I will let you as an exercise. This part I will not do. With the above operations, S inverse R is a ring. Show that, now the problem is show that there is a ring homomorphism phi from R to S inverse R such that, so this is, you can think of the first problem on this, such that phi of S is a unit in S inverse R for all S in S. Okay, so how do we show this? Solution. The map is very easy to define. So define phi from R to S inverse R by sending phi of A to be A by 1. So why is it a ring homomorphism? What is phi of 1? This is 1 by 1, which is the 1 in S inverse R. So this is okay. What is phi of A plus B? This is A plus B by 1, which is A by 1 plus B by 1, which is phi of A plus phi of B. So this is okay. What is phi of AB? This is AB by 1, this is A by 1 times B by 1. Remember the definition of multiplication and addition in this ring. A by S plus B by T is AT plus BS by ST. A by S times BT, B by T is AB by ST. So this is phi A times phi B. Okay, so this is also okay. So this shows that phi is a ring homomorphism. I am leaving the verification that phi is a S inverse R is a ring to you. So this is an exercise for you. Now suppose small s is in capital S, then phi s is S by 1. I want to show it's a unit. Note that 1 by S is an element of phi inverse R, S inverse R, because S is an element of capital S. So this implies S by 1 is a unit. So this is the other statement here that we are asked to show. So phi of S is a unit for every S in S. So also show that, I should also left it, should have written it here, show that phi is injective. Phi is injective. Actually I should have said this, so maybe I should write it here. Most of the time we are going to assume that S does not contain 0. Somewhere I wrote this. Also assume that, otherwise I get into problems. Assume that 0 is not in S. So assume that everywhere 0 is not in S. So show now that phi is injective. So why is that? Phi is injective because suppose phi of A is 0 for some A in R. This implies A by 1 is 0 because that's the meaning of phi of A. Phi of A is A by 1. So A by 1 is 0. That means 0 can be thought of as 0 by 1. That means actually, yeah, so this is 0 element is 0 by 1. So that means A is 0. Okay. So to do so actually one thing that I did not, that's hidden in this exercise, you want to show that this is well defined, this addition, because A by S may be equal to A prime by S prime. But then when you replace that by A prime by S prime, you want to check that what you get is same. So hidden in this exercise is to, you are also required to check that this addition and multiplication are well defined. So that's hidden in here. Only after you check that they're well defined, you can start verifying that the ring axioms are satisfied. So just to maybe start the verification, I'll do the following. So remember what we are doing is A by S plus B by T is AT plus BS by ST. This is the definition. But suppose A by S is equal to A prime by S prime. That can happen, right? Because rational numbers have various representations. 1 by 2 is same as 2 by 4. So then we want to check that A prime by S prime plus B by T is equal to A by S plus B by T. This is required for well definedness. But what is this? This is A prime T plus BS prime by S prime T. This is, and the question is whether these are equal, AT plus BS by ST. Remember, this happens if and only if A prime T plus BS prime times ST is equal to AT plus BS times S prime T. This is what we want to check. But we are given this A by S is equal to A prime by S prime. That means, so we are given this, that means AS prime equal to A prime S. So that means this we know. And now you can just expand this out and you see that using this fact, we can get this fact. So you check this. All you need to do is multiply this out and cancel some common terms and you will get what you want. So that I will leave you to check. So this shows that it's well defined. Now the second part of the exercise I want to check is, let's take R to be Z and S to be Z minus 0. This is our model for the localization. Then we have to verify that actually what we get is S inverse R is equal to Q. Okay, this I will not do all the details, but it's clear what the map should be. Send S inverse R to Q in the following way. A by S should go to A by S. Remember, A and S are integers here, right? And S is not 0. So A by S is actually a rational number, is a ring. So, and this map is a ring isomorphism. So the more general process that we define now for any integral domain and any multiplicative set in it contains within it as a special case the well-known construction of rational numbers from integers. So this I will leave as an exercise for you, not very difficult. So that's not surprise. It's not surprising that it generalizes the well-known construction of rational numbers from integers. So let me do now one more problem and then we'll connect it to the localization. And this is a very simple problem. So let's write it here. Let R be a ring. Let I be an ideal of R such that if A is in R and A is not in I, then A is a unit. Show that I is the only, I is a maximal ideal and it's the only maximal ideal. And it is the only maximal ideal of R. So such rings are called local rings. So it is an ideal, it is a maximal ideal and it is the only maximal ideal. So let us prove this. Very easy. First of all, I is maximal. Why? Suppose I is contained in J and it is not equal to J. So choose A in J, A not in I. Right? If J is a strictly bigger ideal, it must contain an element which is not in I. But by hypothesis, what is the hypothesis? Every element of the ring which is not in I is a unit. So A is a unit. But then 1 belongs to J because A times something is 1, A is in J, so 1 is in J, so J is R. So any ideal that strictly contains I must be equal to R. The next part is I is the only maximal ideal. Why is this? Suppose J is any ideal of R, implies I claim J is contained in I. I claim that every ideal of proper ideal of R is contained in I. Why is this? So if suppose J is not contained in I, that means there exists A in J, A not in I. By definition, if J is not contained in I, that means J is not a subset of I, it must contain something that's not in I. By the above argument, that means J is in R. Okay, but we are assuming J is not in R. So every proper ideal of R is contained in I. But this means I must be the only maximal ideal, right? Hence, I is the only maximal ideal. Why is this? This is because if there is another maximal ideal, we know it is a proper ideal, but then it must be contained in I. But a maximal ideal cannot be contained in I, a bigger ideal. So unless it's equal to I. So it is equal to I. So in no other maximal ideal can exist. So there is an important definition for you. A ring R is called a local ring. So this notation is related to algebraic geometry, where such things are studied. R is a local ring if it has only one maximal ideal. Every ring has a maximal ideal. By Zorn's lemma we proved earlier. If there is exactly one maximal ideal, it's called a local ring. What are examples of this? So this is part of the exercise that I will do, and in fact I will leave many details to you. Let's take R to be Z and S to be the set of odd numbers. In the first beginning of this video, we showed that this is multiplicative. Show that S inverse R is a local ring using the previous exercise. Why is this? So first of all, consider the following set I in S inverse R. A by S in R such that A is even. So one can check that I is an ideal of S inverse R. So it's a subset of S inverse R. It is in fact an ideal. Why is that? 0 is there. If you add two things, AT plus BS by ST, if A is even and B is even, AT plus B is also even. So this is an I. Similarly, if A by S times any element, so if in this case both are in I, now suppose this is in R, S inverse R, and this is in I. This is AB by ST. But if B by T is in I means B is even. So AB by ST is also in I, because if B is even, AB is even. So this is an ideal. And now take an element that's not in I. So let A by S be in S inverse R and not in I. Then by definition of I, A is odd, right? So here I am suppressing some things. There could be several representations of A by S. Nevertheless, for all of them, the numerator will be even, or for all of them numerator will be odd. Because for example, in this example, what is an example of things in I? So 2 by 7 is in I, right? Because the numerator is odd. But 2 by 7 may be also written as 6 by 21 by multiplying by 3 both sides. But even if you use the representation 6 by 21, the numerator is even. You can never write this with an odd number on top divided by another odd number, because 2 by 7 cannot be equal to another odd number by odd number, because when you cross multiply, one will be even, other will be odd, so which cannot be which cannot happen. So this is well defined. I am suppressing that here. So you can ask in the discussion forum any questions about this or work it out for yourself, but this is a well defined ideal, well defined set. So now if something is not in I, that means A is odd, because if A is even, then it will be in I. So that means S by A is in S inverse R, right? Because if A is odd, we can consider S by A. So that means A by S times S by A is 1. This means A by S is a unit. And by the exercise that we just did, S inverse R contains exactly one maximal ideal. Right, because we have found an ideal I, and also it's not equal to R, I should say. Also, I is not S inverse R, because for example 1 by 1 is not in I. Not in I, yes. It is a proper ideal with the property that everything outside it, if you take A by S that's not in it, it is a unit. And by the problem that we just did, if you have a ring and an ideal, proper ideal in that ring such that everything outside it is a unit, that proper ideal is the only maximal ideal of that ring. So S inverse R is a local ring. So this is an example of a local ring. Also another example is every field is a local ring, because field has exactly one maximal ideal, namely the 0 ideal. And just to finish this, Z is not a local ring. The ring of integers is not a local ring. This is because it has several maximal ideals, 2Z, 3Z, 5Z and so on. So I am going to now just do one final exercise to list some of the examples of rings that we have studied. So the final example that I want to do, maybe this is the fifth problem, final problem. Determine if the following rings are Noetherian. Remember, Noetherian means ascending chain condition on ideals exists or every ideal is finitely generated. Integral domain, which I will denote by ID, UFD or PID. Determine if the following rings have this property. So let me just, this is mainly to summarize the rings that we have studied. So I might forget some of them, but I'll try to do as many as I can remember. Z, so Noetherian, so I'll write Noetherian, yes. Integral domain also yes, right, because this is our first example of integral domain. We have shown that it is a PID, so hence it's a UFD. So it has all the properties. If you take ZX, this also all 4 properties. It is a Noetherian ring, it is integral domain, it is UFD, it is PID. Any field, all 4 properties. So these are all simple examples, right? A field is Noetherian, it is integral domain, obviously, it's PID, UFD. It has only 2 ideals, so there is no problem there. What about if R is an integral domain, and R is Noetherian, what about Rx? This is an arbitrary ring which is integral domain and Noetherian, then this is Noetherian, right? This is also integral domain, you can check, because multiplication of 2 non-zero polynomials will give you a non-zero polynomial. This is okay, but what about UFD or PID? That's not clear unless you assume similar conditions for R. So R is UFD, suppose I assume, then this is also UFD. R is integral domain, Noetherian, UFD, then it's a UFD. But if R is PID, Rx is not necessarily a PID, right? Because, so take it R, which has all the four properties that we are interested in: Noetherian, ID, integral domain, UFD, PID. Polynomial ring in one variable inherits three of those properties. It is Noetherian, integral domain, UFD, but not necessarily PID. What is the example? The simplest example is ZX. Z is Noetherian, integral domain, UFD, PID, but it's not a PID. So this is the property of being a PID is not inherited when you attach a variable. So again, these properties will carry over to polynomial rings in any number of variables, finitely many. These are Noetherian, ID, UFD, of course not necessarily PID, as we showed in the one variable case itself. And these are important theorems, right? This is Noetherian part is Hilbert basis theorem. ID part is easy, this is just a simple calculation, and UFD is also requires proof. What we have done is for R equal to Z, and in those videos I said the proof more or less carries over to any arbitrary UFD. Okay, so this is let's say B, C, D. Let's do one more example, some more examples. What about Z adjoined square root minus 5? This is Noetherian, ID, but not UFD. If you recall in the videos when we discussed UFDs, we showed that this has factorization but it terminates, but it's not unique. 6 can be written in two different ways as product of irreducible elements. Once it's not UFD, it cannot be PID because a PID is a UFD. Next example. Okay, some of these are not immediate, one has to check. So what I will let you do is, this is Noetherian. Because this is a polynomial ring in one variable, three variables, modulo and ideal. So image of a Noetherian ring is Noetherian, and the ring ZXYZ is Noetherian. So when you quotient by this is the image of ZXYZ, so it's also Noetherian. ID requires a proof, and let me not do that for now, and we can discuss it in maybe discussion forum. This is an irreducible polynomial, that one has to show. You cannot write this as a product of two polynomials, so it's irreducible, so it's an integral domain. It's not a UFD, and the reason is x bar y bar is equal to z bar squared. So these are two different factorizations. So these are two different factorizations. So this is not a UFD and hence not a PID. So one has to check this. What really one has to check is that x bar, y bar, z bar are three distinct irreducible elements. That's not that difficult to check, but I will leave that for you. G, ZXY mod XY. So this is Noetherian because again ZXY is Noetherian by Hilbert basis theorem. ZXY mod XY is a homomorphic image of ZXY because there is a unique surjective map. There is a natural surjective map from ZXY to ZXY mod XY, and image of a Noetherian ring is Noetherian. So this is Noetherian, but this is not an integral domain, and hence now not UFD PID also, because UFD PIDs are D there stands for domain. So something that's not an integral domain cannot be UFD or PID. Why is it not a ID? Because x bar and y bar are not 0, but x bar y bar is 0. So when I write bar, I mean simply the images under the natural map from ZX to ZXY to this, the residues of x and y. What about so the next example, So this is an example of something that's not even an integral domain. So one more example. So the ring that we consider S inverse R, S inverse Z, where S is odd integers. The previous problem that we considered. Here S inverse R, one can check. So S inverse R is Noetherian. See, there is only one ideal here, right? One maximal ideal. And actually I'm not saying that there is only one ideal. There are many ideals, but only one maximal ideal. And one can check that every ideal, actually I have proved that there is only one ideal, one maximal ideal. Check that there is only 3 ideals. 0, the ideal I from last problem, which is A by S, where A is even and S is of course odd, and S inverse R itself. There are only 3 ideals. These are the 3 ideals. So now Noetherianness can be checked because one equivalent condition for Noetherianness is every ideal is finitely generated. Here of course there are only 3 ideals and they are all finitely generated. I can be written as the ideal generated by 2 by 1. 2 by 1 generates it. So one can check this. This is an exercise for you. So it is Noetherian. It is an integral domain and it is PID actually, because every ideal is principal here. There are only 3 ideals. 0 is certainly principal generated by 0. S inverse R is certainly principal generated by S inverse R, and I is generated by 2, S inverse R is generated by 1, I is generated by 2, 1. So it's a PID. So it is also a UFD, and one can check that it is an ID. Of course, that is required to verify the D part in UFD and PID. So this is an example of another ring which is Noetherian, integral domain, UFD and PID. And let me just give you a final example where something which is not even Noetherian, for example, if you take Z adjoined x1, x2, infinitely many variables. This is not Noetherian. Okay, the ideal generated by all variables is not a finitely generated ideal. Similarly, it is though integral domain. Okay, so it is integral domain. It is also UFD one can show, but not PID. Just like you can show unique factorization for polynomial ring infinitely many variables, you can show it for infinitely many variables, because to determine unique factorization you only look at one specific element. You take a specific polynomial, it only involves finitely many variables. So you are really working in a finite polynomial ring, which is a UFD. It is certainly not PID because you attach 2 variables, it's already not PID. It's not Noetherian. Similarly, one more example that we looked at was 2 second power of 2, fourth power of 2. It's not Noetherian. It's integral domain, UFD. It's actually not UFD. That was one of our example, right? And of course not PID. It is not a UFD because we constructed this ring to show that factorization does not even terminate in this ring. Okay, so in this case it's not even a UFD. So these are the examples of some of the rings that we discussed in this ring theory part of this course, and I wanted to list all of them because and with respect to the 4 properties that we emphasized here: integral domain, Noetherian, UFD, PID. So I hope these are clear. Please go back and see this video again if you have anything that's not clear, and you can ask questions about this. So this completes the discussion on ring theory. In the next video we are going to start talking about fields. Thank you.